All right, so welcome everybody to our final design review here. We'll get started any second now. Keep loading. All right. So between myself and our design lead, Stephen Lyons, we came up with these goals for our car. So we wanted to reduce the weight from our previous cars down to 435 pounds of dry weight. We also wanted to reduce manufacturing time and effort in the effort to get more driving time, and the whole end goal is to increase design and event scores. So next up is our chassis lead, Daniel Horner, and he will be going through his system. We'll be holding off till the very end for questions. We're going to go through all the presentations first.
Hello, my name is Daniel Morishita-Horner. I am a third-year mechanical engineering student, and I'm the chassis team leader. So again, in keeping with the whole design theme of reducing weight, I've determined that reducing weight to the 435-pound goal will decrease lap time by 1%, which is around half a second in terms of the 60-second course. Lowering the CG, the new chassis will lower the CG. This reduces the lateral load transfer, which also decreases the lap time. And then finally, with improving manufacturability, which shortens the build time for more testing and driver testing, because the driver is a crucial element in the points. So OR15, which is the gray car out there, is 522 pounds with a chassis of 78 pounds. The red car, last year's car, is 478 pounds with a 75-pound frame. I'm hoping for the 435-pound car with a 60-pound chassis, which is around a 30% or a 15% weight loss in the chassis. So how I would achieve this? I will achieve this using a hybrid monocoque and space frame chassis. So the space frame chassis part will begin from the roll hoop back. We'll eliminate the rear box section where the diff is, which we currently have in the 15 and 16 car. So the monocoque portion will be an aluminum carbon fiber honeycomb sandwich panel, which will be cut and folded into place. And lastly, all this will redistribute the weight for more rear percentage and less change between drivers. For example, one of our drivers is 200 pounds and another one is 150 pounds. So it centralizes the driver's CG on top of the car's CG. So here's a rundown of the chassis and body system weight. So as you can see, the big, so it's like 95 to 67 pounds if you include parts of the body. So since it's a monocoque, I do not need a nose cone. So a nose cone is like 7 pounds. The belly pan is around 3 pounds. It all adds up, and this represents a 30% weight loss. And this gets us almost there to the 435-pound goal just in my system. So the rear chassis is going to be unchanged, 4130 chromoly steel, welded by Trent. I chose 4130 over 1010 or 1018 because it's equal weight, greater ultimate tensile strength and yield strength given the same cross material. And then currently we have square bars, as we've had for several years, in the rear for suspension, and we will move towards round bars because it's a more efficient way of having the loads go into the chassis. And we will not, we don't plan on normalizing the chassis. Previously testing have shown that it's not overly brittle when we weld. So our rear design, our constraints are basically the same suspension geometry, same engine configuration intake. I did lower the engine by 1 inch, and the engine weighs 20% of the vehicle, so that reduces the CG of the vehicle by 0.2 inches. We improved the differential mounting, which will be lighter and stiffer and more easily accessible to remove, especially since this year we have a diff that we can actually adjust. So we will have to do that many times. And then I moved the rear wheels forward to increase the rear weight bias, because right now we're at the 52% weight in the front with a driver. Our goal is kind of in the 48 front. Suspension pickup points on nodes. So this decreases the deflection by 15%. Currently our pickup points are not at nodes, so that induces a slight bending into the chassis, because for the chassis it's basically you want everything to be in tension and compression for the bars. So again, this illustration shows the pickups not on nodes in the first picture on the left. The differential mounting on the right, we'll talk about more later, but in that setup, in order to change the front to backward location of the diff, you have to shim the differential in like 2 axes. And then there's plenty of room for lowering the engine, as you can see, as there's no bars underneath the engine. That's how I lowered the engine by 1 inch. So here's a basic idea of the frame for this year. And then previously we had pushrod rear suspension, but we're changing to an overdriven shock in the rear, which will attach to this node right here. As you can see, the suspension loads are in line with the A-arms, which we didn't have previously. And we will jig in this manner, and as far as the pickup points, we will jig by previously making the upright and A-arms and using those as the jig. So for the more exciting part is the front material selection. So my inspiration came from the Lotus F1 car from the 1980s, and after more digging around I found some European cars that do the same process. So basically it's a honeycomb structure which forms a shell as a strengthening part of the chassis. It consists of aluminum honeycomb core, which is 30 millimeters thick, and 0.5 mil skins, as well as unidirectional carbon fiber on top in order to gain the equivalency for 1.065 wall 4130 tubing. So basically the idea is to increase the second moment of inertia of the material, and as you can see, for a little penalty in weight you almost triple the strength and quadruple the stiffness. So how I first determined the panel using basically these equations, and that's how I made my initial material selection. And then my final material would be this honeycomb right here, which consists of the previously discussed 1 layer of unidirectional and then a spread toe carbon fiber on top in the 45-degree layout. So this is my test results. As you can see, the blue line is this panel right here, and the orange line is the 1010 1/065 wall. So I have to prove equivalency for that bar. So the peak load was a lot greater, and most importantly, the energy absorption was greater, which 82 joules versus 71 joules, as well as the stiffness was greater as well. So the derived material properties, most importantly, would be the EI, which is the buckling modulus, which is the Young's modulus times the moment of inertia of the panel. And for different areas of the car, I had at least 1.3 times greater than steel. So for the new chassis, it would be a lot safer in the unfortunate incident that we may hit something. And I chose the aluminum honeycomb because it was the obvious choice for availability and cost, as well as these material properties. And here's the basic shape of the car. So I have the rear section as mentioned before. Now we have this kind of step up where your legs are. This reduces the CG of the driver. So last year we had a 32-degree seating angle, and now we have a 45-degree seating angle. And although that increases the CG a little bit, actually we have a total net decrease in CG by 1.5 inches, because now the driver sits lower. So the driver used to sit like right here, and now he sits over here. And then I move the CG rearward by 1 inch, which is closer to the CG of the vehicle. And here's the comparison between last year's car. I have this elimination of the rear box, eliminated this approximate section. And then mostly everything else I try to keep the same dimensions. Except for the front's a lot narrower as by the top-down view. And then after talking to some drivers that we have, including judges, they had very little elbow room in the cockpit area. But now I have increased the cockpit room, so it's basically 24 inches from side to side all the way towards the front of the car. However, I do need inserts for any pickup points, and these are the loads that they have to take. I'm still working on this as I need to use a lathe to do this and do material testing. I will conduct torsional rigidity tests later. I have written a MATLAB program to determine the lateral load transfer distribution for varying torsional stiffness, and that also takes into account the static weight distribution as well as the stiffness of the LLTD. And how I will construct this, I will route a section of the panel, and then I will fold it in this manner, and then I will jig it like that, and then it will form into shape, so it's easy manufacturability. Timeline, chassis arrives in 2 days, the rear half. I ordered the honeycomb today. It will come in 2 to 3 or 4 weeks, and hopefully we will have the chassis done by our deadline of first week of February. And that's it for chassis.
Up next is Stephen Stanfield with suspension.
All right, so how y'all doing? I'm Stephen Stanfield. This is gonna be my third year on the team, and I'm the suspension team leader for the second year. This will be my second year. So the overall goals of the car were to reduce the weight from 487 to 435 pounds, to reduce manufacturing time and effort, and this was at the cost of adjustability, at the cost of resources, and reliability and serviceability. So the way that I'm going to accomplish these goals on the suspension system, the main changes that we're making are we're switching from a single lug hub to a 4-lug hub. We're going from a CNC'd aluminum upright to a welded steel upright, and we're keeping the same kinematics that we've had since the 2014 car. So one of the largest changes that we're making is going from a single lug hub to a 4-lug hub. This will mean that we have to use different wheel centers, but in previous years the team has already used hubs or wheel centers with this bolt pattern, so that will allow us to already have, I believe, 4 sets of functioning wheels that will work on the 2017 car. By going to a 4-lug hub design, we get rid of the single lug that was it wasn't as stiff as it could have been because it was a smaller area, and in doing this we'll use larger bearings in the front. We'll make an overall larger part in diameter, but the weight will be less. So if you look, the old hubs in the front were 1.17 pounds and 3.7 in the rear. And the new hubs will be 1.09 pounds in the front and 1.56 pounds in the rear. Between the 4 corners of that car, that's going to save us a little over 5.5 pounds. And in addition, the larger diameter allows us to have greater stiffness. We're going to see about a 30% increase in stiffness in camber. So the other big change is the elimination of the rear box that Daniel was already talking about. This is going to make the geometry of the rear A-arms change. The members of the A-arms are going to be facing a little bit more forward. They're going to be farther forward on the car in order to keep the same wheelbase of 60 inches. And in addition, we're downsizing the bearings on the chassis side on 3 of the 4 members in the rear. This will save us a little bit of weight, but because they're not the same bearings, they don't have as high of a of a working angle, so we have to turn them 90 degrees to keep them able to function in the way that they need to. So that's the A-arm geometry that you see on the left. On the right, the top picture is the bearing housing on the chassis side, and then the bottom picture is what will function as the pickup point in the front on the aluminum monocoque. We will have 4 of those. They'll be positioned upside down, so the opposite of what you see right now. And those will function as our keels to keep the front lower A-arms mounted where they are in the 2015 car, while we're still able to raise the floor on the 2017 car. The uprights, like I said before, they're going from a CNC'd aluminum to a welded steel. This is going to hopefully decrease manufacturing time. It'll allow us, if we have any issues with the upright, if we see bending, breaking, anything like that, we'll be able to simply weld them instead of having to CNC new ones. The upright geometry is the same as the 2016 car, but we're going back to a welded steel design like the 2015 car with a couple of improvements. One of the biggest issues with the 2015 car was it used a welded-in nut on the bottom. I'm getting rid of that by leaving the lower member on the upright. It's going to only have sheet metal on 3 sides, and this will allow you to not use a welded-in nut, so that if someone does strip a nut while putting the upright on, you don't have to cut it out and weld another one in. Other than that, we're going back to steel because steel and aluminum have similar stiffness to weight ratios, so we can keep the same stiffness and very similar weight to the aluminum ones that we designed last year. And that's all I have for you right now.
All right, up next is Mathew Burgos with Powertrain.
How you doing? I'm Mathew Burgos. I've been on the team this is my 2nd year, and actually also my 2nd year on Powertrain, Drivetrain, but this year I'm leading it. The basic engine design is going to stay the same as previous years. For anybody who doesn't know, it's a 2005 Gixxer 600. It's a 6-speed gearbox from a motorcycle, uses a wet clutch, and is a 610cc after we bore it out. The engine's internals are Carrillo connecting rods and diamond pistons. Also, the cylinders are Nicoseld. The cams we use in the engine for this year are going to be a custom grind from Jones Cams to keep our torque curve pretty flatlined. Also, the head is going to be port and polished by John Kazi Racing. The intake design for this year is going to use the same basic intake that we've been using for the last 3 years, with some minor changes. The minor changes are going to be this outside ledge that's around here, which usually has bolts in it, is going to be epoxied. That's going to reduce the weight in the intake manifold. Also, the bungs, which hold the injectors, are going to be angled more downstream, so we have a better injector spray into the engine. A new restrictor is going to be CNC machined this year. The exhaust design. To reduce weight in our exhaust this year, we're going to move to an Inconel header from Profab. Also, with the new chassis, we have to reposition the exhaust to fit with the chassis, and also use a dual muffler design because in previous years we actually lost 15 horsepower in the muffler because of all the back pressure. So utilizing dual mufflers, we can allow more flow and open up the mufflers a little bit. I haven't figured out what type of mufflers I want to use yet because we don't have a running engine on the dyno to do testing. The cooling system is pretty much going to be a single large radiator. In the past, we've used 2 smaller radiators, but to balance out the weight for the mufflers being on the side of the car, we're going to put 1 single radiator on the left or right side. Haven't decided yet. Drive chain is a 520 motorcycle or dirt bike chain. Also, final drive ratio is 1138. The diff carriers also needed to be redesigned this year to fit without having the rear box, and also to make it so it is easier to remove the diff, because our differential this year we're using is the Drexler, so it has three different adjustability modes for driving. So it needs to be removed out of the car to be adjusted. So it needs to have a single shim to allow it to be easier removed from the car. This year's decrease in weight through the drivetrain is going to be 11 pounds, because the Drexler differential does weigh 50% less than the differential we're using in the car now, which is the Taylor Race. Also, the diff mounts are smaller. Utilizing the smaller diff mounts, we are also losing weight in the mounting system for the differential. And there's some more weight savings, less hardware, also smaller bearings. There's a picture of the diff mounts. So my build timeline is 1 month for engine. The building of the engine shouldn't take a month, but we definitely need a month of testing on our in-house engine dyno. Also, the diff mounts will take about 4 days, because they will need to be water jetted and then finished up on the mill for bearing fitment. Also, the cooling system, around 6 days to just assemble the cooling system, and we are also going to do some dyno testing with different radiator sizes. Intake is about 2 weeks. Lay up the carbon fiber and assemble the intake. And the exhaust, once the headers are shipped in, we'll have to weld them together. That should take about 2 weeks.
All right, thanks, Matt. Up next is O'Brien with brakes.
Hi, my name is O'Brien Lavin, and I'm doing the brake system. Now, starting off with the pedal, the one on the left side is the one we've been using for the past couple of years, and the one on the right side is going to be the new design, and it's going to be made out of 6061 aluminum, and I was able to reduce the weight from 0.85 pounds to 0.75 pounds. And the reason for redesigning the brake pedal is because we're going to be going with a more vertical master cylinder setup to gain better mechanical advantage. And we've already tested it on the OR16 car that we have, and we went from 750 psi to 1350 psi, which is about a 600 psi increase just by changing the geometry of the pedal. And we'll be going with the Tilton 77 master cylinders and the Tilton brake bias, and also steel braided lines for the brakes. Now for the rotor, the main design change is where it mates with the hub. We're bringing the hub up higher to cover each side of the rotor where it mates at the bobbins, to pretty much take the bobbins out of shear and all the stress off of them. And it's going to be symmetrical on each side, so for manufacturing purposes, we don't have to worry about if it fits on the left or the right side. We can just put it on either side. And all 4 rotors are going to be 8 1/4 inch all the way around, changing from 6 1/2 inch in the front last year and 9 1/2 inch in the rear last year, which it'll just be about 0.2 pound increase in weight this year just for the rotors. And we'll also be switching from the material from steel to iron, and the 2 types of iron that I'm going to be testing are gray iron and stronger ductile iron. And the benefits of the gray iron is a higher thermal conductivity and better dampen for the vibrations, but the ductile iron has more tensile strength and yield strength and the fatigue resistance. So if the gray iron doesn't hold up, then I'll switch to the more ductile iron. Now for the calipers, we've been using the Brembos, which have a piston area of 1.25 inches, and we'll be switching to the Willwoods this year for essentially the same piston area, but they're also 0.4 pounds less in weight each caliper. so we'll be able to reduce weight that way. So the overall design goals for the brake system is to reduce pedal weight, less pedal effort, lighter calipers, but also have the same piston area, and increase rotor temperature by switching to iron. And the overall predicted weight reduction is 1.6 pounds, so we can make a more lighter and efficient brake system.
All right, thank you, O'Brien. Next up is Steve with electrical.
Hello everyone, my name is Steve Gaillot. This is my second year with the team. Last year I was asked to take over the role of engine lead. And I guess this year I decided I was a glutton enough for punishment that I thought I'd put myself in this role. So this year's design goals for the electrical system are the same as ours. It needs to be reliable, it needs to be weatherproof, it needs to be as lightweight as possible, and I'm trying to introduce some bit of serviceability this year. Basically, the benchmarks are last year's wiring harness. Stephen Lyons, last year's electrical team lead, did a bang-up job with selecting materials and connectors and all that. And with mil-spec wire, you really can't beat it. It's a fluoropolymer-coated, high-strength copper. It's used in satellites. It's used in airplanes. You really can't beat it, and it is primarily responsible for why we're able to get the weight and bulk of the system down as much as we can. Automotive connectors we're kind of stuck with because that's what automotive sensors take. Here's a brief system overview. This is the MS4 box and where it ties in with everything on the car. Obviously, there's a lot to go over. One thing I'd like to talk about is the shifter mechanism. We talked briefly about going back to a pneumatic-driven system. We decided against that because it is one more system to have to service. If you lose your air, you're done, whereas electrical, you always got electrons in the battery, you hope. With the data acquisition system also staying the same, we already have it. It's a cost we don't need to add into this year. It's an off-the-shelf AIM system that basically we already have the pieces for, so that just kind of shoehorns in around everything else that we've done. The different system interactions, electrical is kind of the nervous system of everything. It ties everything together, so it's not the place to try some wild and crazy designs. You just wanted to interface with everything and do what you needed to do. So I kind of covered a lot of this already. So yeah, the aim is staying the same. The one thing we did want to add this year was onboard EGT, which we already have the module for. I believe we need to get to some sensors, and the current shunt, which I'll get to at the end. We also had to modify some cam and crank triggers last year to make the Bosch MS4 standalone ECU work with that engine, because the crank and cam triggers are a little bit different. This is an example. This is the crank trigger that we had to modify. So again, it interacts with a lot of different systems. It has to be identical with OR16, and that is primarily, as far as the serviceability, I want the engine side harness to be identical to last year, so we can build a couple of them, and then the harness can stay with the engine. So as we're pulling an engine out of the car, putting on the dyno, swapping things around, we spend a lot of time just with little connectors and clamps and everything removed. It takes about 3 hours, I'd say, to pull a wire harness off, swap the engine, and then another 3 hours to put the harness back. We're trying to eliminate that. So again, kind of trying to repeat what we did last year in multiple. Dynamometers, we're going to spend a lot of time this year. We got some new spaces. We're going to be building that out and doing all similar wiring to the car in there, making it a little bit more official, a little bit safer. And then tuning is where we're going to be spending all that time on the dynamometer. Last year, Matt, myself, and Stephen Lyons spent a lot of time on the dyno, kind of figuring out what we're doing, using the Bosch software, using the AIM software, using the dyno software. So there's a lot there, and this year we're hoping to just kind of define and refine the process. Cockpit controls, Thor will cover, but basically the only thing I want to add there is a steering wheel disconnect, because it seemed like a major failure point to have a tether there when you're doing the egress, we're throwing the wheel out, somebody's having to catch it, and if that wire gets cut, we're down for a good bit of time. And then the current shunt, this is something I want to add. I'm looking for the right current shunt monitor, a small IC that will convert the millivolt signal into hopefully a 0 to 5 volt to tie in with the data acquisition system. It'll give us a little bit more current information as far as what's going on with the electrical system over just kind of measuring in ohms and doing the calculations. We should be able to put that anywhere we like and get a little bit more information than we had last year. And then traction control. We paid for this last year. It's a licensed module on the ECU, but we didn't get a chance to get it tuned properly. So again, back to the tuning, we want to be spending a lot of time. This is basically looking for a difference in wheel speed, slip percentage between the front wheels, the driven wheels and the non-driven wheels. And then as far as timeline, planning is ongoing. It's electrical, so we're not really designing parts. We're just gathering part numbers and everything. And then construction, I figured 2 to 3 weeks each for the engine harnesses. Chassis harness, 2 to 3 weeks once we get the chassis here. And the dining room is, I think, about 2 or 3 weeks to get it going, and then modified as need be. And that's all I have. Thank you.
All right, thanks, Steve. Up next is Chris Branfield with Ergonomics.
Hey guys, doing? I'm Chris Branfield. This is my 3rd year. I'm a mechanical engineering student. Also my 3rd year on the team. 2nd year as cockpits controls leader. Yeah, let's just dive into it. So the goal is just like everybody else has already pointed out. We want to reduce weight. That also lessens the moment of inertia. We get faster laps, more points. We optimize manufacturability, more testing time, more time in the seat, faster lap times, more points. Increased comfortability, faster driver, more points. Materials testing, predictability, safer car, increased understanding, more points. So here's like an overview of what weight I'm going to be losing in my system. We can neglect firewall, that's something to talk about. So I'm looking at a 4.6 pound reduction in my system. To first start out with is the seat. The seat, we're going from 12 layers of carbon fiber to 12 layers of just carbon fiber to a 2-ply, so 4 layers of carbon fiber balsa wood sandwich construction core, so it's gonna be like a panel. We're going from a 3-month project, approximately a 3-month project, to about a 3-week project. Basically the construction of the seat in years past, so 2016, 2015, you would design, print, cut, glue, sand, bubbles, so like that's glass bubbles, sand, high build, sand, layup. And that construction takes a long period of time. We can have the car moving ahead and increasing our testing time. So the overall weight reduction is 2.8 pounds. The material selection I chose was balsa wood. Balsa wood has a high strength to weight ratio, a high chemical resistance. It also is fire retardant, because that is close to where the headers are, and we're getting a lot of heat from that. So I did 2 strength tests with 1-ply and 2-ply. I doubled the flexural stress, which allowed us to, because of the forces in the pedal, because of the rules, there's a 450 pound force limit on the brake pedal, and of course you have a reaction force, of course, with the driver's weight. With the flexural stress, I was able to stay within that window and a factor of safety. With the headrest, we're actually going to be gaining a little bit of weight in the headrest. The only reason being is the headrest was put in a moment because of where the driver's head was. It was below the mount, so it was causing there to be a moment in it and a lot of flex. So when the judges decided to go over there and push on it, they did not like that very much because of the structural. So I'm going to fix that. So that's going to gain us more points. So we're not going to have an adjustable pedal box this year, but it is going to be a different construction than last year. It was mounted to two 1-inch bars, and now it's going to be mounted to the floor of the aluminum monocoque. Little difference is now it's going to be cut and pinned. So all that so it's going to be CNC water jetted, I believe 4130 chromoly steel plate. That's going to be water jetted, that can CNC'd. So that can be constructed within a week's period of time. So this is an overview of the pedal box weight. As you can see, with the pedals, so that's on top of something else. So the pedals, the gas pedal and clutch pedal, weigh about 0.4 pounds. I'm trying to go with a carbon fiber balsa wood construction, which is going to allow us to reduce weight. I believe the pedals are 0.07 that I got theoretically for a balsa wood carbon fiber pedal. We're going to be doing strength testing, so I'm going to make a CNC plate out and make the pedal and do a brake test and a fatigue test to get the proper factor of safety. Definitely for a gas pedal, I'll be able to reduce that 0.4 pounds. For the clutch, it's still questionable. We were getting 7 pounds to engage in the gas and 70 pounds to engage in the clutch. So, which is bad. We need to check that out and figure out what's going on with that system. So I'm trying to go with both, but as of right now, it's going to be the gas pedal. Another few things that I'm going to be changing to is going from quarter 28s to 1032s, as well as going from ball bearings to bronze sleeve bearings. That's reduction in weight. Reduction in weight. So, on to the next one. And another thing I'm changing this year is doing the steering wheel assembly. The paddle shifter assembly is 0.7 pounds, and by building it into the steering wheel, I'm going to be able to get rid of that weight. On top of that, the dash. So we have the G dash, which is part of the Evo 4. So we're going to be getting rid of the G dash and substituting in a monitor for simple things. We're going to be using the G dash for testing, so we get all that information there, and having the substituting for competition to lose that 0.7 pounds. So that's going to be one of the biggest changes. So here's an overview of the weight for the dash. And the time frame, this is one of the biggest things, manufacturability. Like I said, the seat is going to go from 2 to 3 months to 2 to 3 weeks. The headrest is about 1 week because most of it's water jetted. Pedal box assembly is about a week because it's water jetted as well. And the steering wheel is going to take a little extra time, and it still needs design work and stuff like that. So that's the end of my system. There's a little summary of the weight. Okay.
All right, thanks, Chris. Up next is Max with Aero and Body.
Alright guys, my name is Max. I'm the team lead for aerodynamics and body. And this is a presentation. System goals. Alright, so this is going to be our first year running an aero package. Our primary goal this year is to get a good body. This is kind of like the prototyping phase for aerodynamics. We're going to get as much as we can done this year. Best case scenario, we run a full aero package. Worst case scenario, we test a full aero package and it doesn't work very well, but that still gives us all of the design that we can use on our design presentations. That'll still help us with points. Either way, the body will be completely done. That is our top priority. So that is going to be a nose cone to cover our impact attenuator. That will also be side pods to cover both the radiator and the muffler and any other things that are necessary. Below that on the priority list, the under-tray and diffuser is next on the priority. There's a very good chance we can have an under-tray running at competition this year. It's something that's very feasible with the team that we have and with the software that we've gotten. So we should be in pretty good shape. Hopefully we'll get a full aero package. We'll see how it plays out as we go along. Testing. The first step to testing an aero package is you need to do simulations. We did get a great sponsorship from Star CCM this year. They were gracious enough to give us a research package that's valued at $70,000. So that's going to be some great software for us to use. It's perfect for all the simulations we need, any type of flow simulations. We can test radiator stuff in there. We'll be testing all of our aero stuff in there. So we're really excited about that. We're going to do 2D and 3D simulations. All of our designs are going to be driven by flow simulations. So we're going to do 2Ds to determine different trends, different inlet angles, outlet angles, stuff like that. Flow angles over the airfoils so we can determine the best airfoils to use. Once we have all that information, we will get into our 3D design phase. We will be designing all of our stuff through SolidWorks. We will be doing 3D simulations in Star CCM as well, and we'll be looking for your lift coefficients, your drag coefficients, the pressure differential, stuff like that. After we are satisfied with our simulations, we will be making some prototypes. We are looking for getting some real on-track testing. We want to do a sweep, a long turn, we want to do a tight turn, we want to do a slalom, see what speeds we can pull. We are also planning on manufacturing a prototype under-train diffuser for OR16 while we're waiting for all of our 17 stuff to come in. So we should be able to get some preliminary testing done. Hopefully before this year ends out, we should be doing some testing with 16 car in December, maybe early January. And then once OR 17 is ready to go, we should have an Aero package ready for 17 to test on that as well. You can see we have some examples. Of course, this is not what it's going to look like. All of our designs are going to be driven exclusively by our simulations. This is just something thrown together, but these are potential airfoils that we are looking at. Star CCM is working out very well. I was able to import geometry, so we're up and running now. I'm running some simulations, so we're making good progress on that. So all of these airfoils will be tested. We'll be pulling up a lot of charts like that, a lot of graphs, a lot of pressures. We'll be able to find out all our information, and we should be able to be finished with all of our two-dimensional simulations by the end of the month. Well, okay, 2 weeks. I forgot, it's the 27th. So 2.5 weeks is what we're looking for. So under tray, that is our top priority. 2D testing, we're looking for the inlet angle, stuff like that. One thing you have to look for in your under tray is it's not going to be flat all the time when you're turning. It's going to be at an angle, acceleration, deceleration, stuff like that. So when we're doing simulations, we are going to need to do many different tests at many different angles, pitches, yaws, stuff like that. That is going to increase time. It's probably going to be the longest thing to test because we're going to have very many tests to do on that. So once we do all those, we will get those up. Also on the manufacturing side, we need to look at stiffness because we're looking to create a pressure differential of maybe 80 to 100 pounds down there. And we need a material that can support that and remain rigid so that we don't suck the diffuser to the floor of the ground. And
All right,
that's it.
so that wraps up the design presentation, but real quickly, Steve has a safety presentation. Being that we are moving into the manufacturing stage of things, we do have to be mindful of all safety things when using the machine shop. So take it away, Steve.
Thank you. Yeah, like Marco said, we enjoyed as a team a tremendous amount of success the last couple years, and we don't want anything avoidable to come and take that away from us. So we decided that this would be a good year, kind of started over the summer. This would be a good year to start, not directly related to design, but a safety team. A little bit more about myself. I'm actually an aviation mechanic. I'm a licensed aircraft mechanic. I have about 15 years in the aircraft industry. Got my start in the military, so I saw a lot of these kind of safety, corporate kind of stuff that nobody likes to sit through. Our goal is to try to find a way to make it fun, make it interactive, and like we say here, we want to model it. We want to establish the culture of safety. We want to model it after industry standards because one thing I've noticed, I am out in the field working, I've noticed that engineers aren't just asked to solve piece part problems, they're also asked to have input into safety programs, quality programs, that kind of thing. And that's something that's often not addressed in school, and I just thought this might be a good opportunity to give exposure to everybody while kind of making us all appear a little bit more professional and growing from each other. And then also to win the confidence of our sponsors and our faculty. So again, we want to model it after industry. Mostly the biggest thing is PPE, safety glasses, personal protective equipment, that kind of thing. But also machine tool safety. I'm going to be working with Fred. We're going to come up with some kind of official training program. We're going to do a lot of that with the other students. But again, first aid, fire safety, CPR. Matt Burgos' dad is a firefighter. He's already agreed to come in and give us some basic firefighting training. We got a lot of guys running around in the lots late at night with fire extinguishers, but we need to have a little bit of training with them just to make it a little bit more official. Hazmat, we want to get a proper hazmat program in place, and then communication and other human factors, which brings me to the Maintenance Dirty Dozen. This is a set of posters that I've seen my entire career, actually, just began in the late 90s. The Maintenance Dirty Dozen were born of the aviation community's growing awareness of human factors in maintenance. You know, you stayed up too late last night, you're out drinking, or your wife left you, whatever. That kind of stuff gets in the way and can really cause safety problems. These posters were born of that, and I actually spoke with the creator of these over the summer, and he agreed to donate them in full to the team. So those are going to be a rotating feature. They're right inside the door as you go up the stairs in our new space, and rather than put all 12 up at once, we're going to rotate them, which the frame is designed for. So a good continual reminder of what's going on. And then again, the formalized training. We want to put this in the students' hands. I intend this program to kind of take on a life of its own and grow. This is my favorite sign, and Fred's favorite sign too. We've seen this in the machine shops. It's just a good one. Think about what you're doing, guys. But yeah, we hope to bring in outside people. We hope to have students kind of take this on and turn it into our own thing. And again, create the culture of safety awareness so that our sponsors can be proud of the product they're putting on, that they're putting their name on, and our our faculty can sleep well at night knowing that we're being safe in the shop because we tend to work some odd hours. So, and then overall, just that Owls Racing employees are professional, knowledgeable, and trustworthy. Thank you.
All right, thank you, Steve, and design leads for all of your. We will now have a discussion or questions and comments. All the leads, please come back up, and if you have a question, please ask now.
Questions?
I'm just staying on the side.
How often you guys up in like 5th and 6th gear in that car?
Generally, with this gearing ratio, we don't ever get into 56.
How come it hasn't been dropped?
We just haven't been able to change that. There's a number of things that are involved in removing those two, but that is something Kazi Racing is looking into for us.
All right, we had one from our YouTube channel from Luca. Any thoughts around compensating for the low-end torque loss that the dual mufflers will cause?
Not at the moment, but it will be once we get the dyno up and running and we get some dyno testing done.
So mostly with the valve time.
Anyone else?
Is there any shifting lights or anything inside the car to know where you are in the gear, what gear you're in, etc.?
That's electrical.
We didn't have one last year. There are lights on the AIM dash that will handle that. They're programmable by color, I believe, and in my opinion, they're a little bit not visible. We're going to be working with Thor. We're going to come up with a nice shift light mechanism. There's also electronic gear shift control mechanism. Lance and I are going to be redesigning that board, and hopefully that'll take care of most of the shifting on its own with an override switch.
Needs to be visible in the day.
Bright as the sun.
Barrett has a question about suspension. He asks, are you still using the giant bearings? Have you looked at smaller ones for weight savings? Also, the upper ball joint mounts are cantilevered sheet metal. Have you tested stiffness on the knuckle, especially versus previous years?
Okay, so the first part with the bearings. This year, 2016, we ran smaller bearings in the front in order to save weight with the upright. But with the larger bearings, we're actually able to make the hub overall lighter. The upright is not much heavier, and as a package, the overall front upright with the smaller bearings is heavier than the new redesigned package for 2017. And then what was? The cantilevered sheet metal. That's the same. They're the same clevises, the same design that we've run for 16. We didn't see any real deflection issues with them. So.
I've got quite a few questions from Barrett. This is regarding drivetrain, a little bit of suspension as well. That is, do you know the maximum allowable angles for your CV joints, and how close are you to that full angle in full jounce?
I don't know how close we are to in full compression or rebound or anything like that, but I know we're limited right now by how far forward we can move the wheels. So we're trying to get more weight over the rear of the car, and in doing so, we're moving all four wheels forward. I think we ended up moving them forward a little over an inch, and that changed weight distribution by a couple of %. But we are limited by the CV joint angles. That's something that we're conscious of. So.
Statically, we have no angle.
Yeah. Statically, we have no front, back, and we're keeping the same geometry as last year, and we have no problems with that.
Okay. He also asks, why not go to smaller tires?
That's something that I've thought about. Definitely going to 10-inch tires, 10-inch wheels. As far as narrower tires, if he was going that direction, we currently run the widest 20-inch tires that we can run. Our car has a number of issues putting power down, and then it has issues understeering in the corners. So it's a fairly well balanced car, but utilizing all the power that we have is our main issue. As far as going down to 10-inch wheels, that's something that I would like to, or I have been looking into. I'd like to I do see the car going that way in the future. Whether or not it does go that way, we'll see. But they say with 10-inch wheels, you can get probably around 30 or 40 pounds out of the car. You're going to get a little bit less grip from the smaller tires, but that's something that we didn't do this year because that would introduce a whole nother level of changes. It's harder to package your uprights and brakes and rotors in the smaller 10-inch wheels, that kind of.
Okay. And then he also wants to know, since you moved the wheelbase forward, did you move the steering rack with that as well?
Yes, the steering rack has been moved. That's something that quite a bit of time and effort has been put into to reduce bump steer when we're moving the floor up and moving the wheelbase forward. So all of that will be taken into account.
Okay. And then this is for everybody from Barrett as well. He wants to know how much of the previous models were able to be reused and modified to design with this year's car. Are you doing any parametric design?
We're not doing any parametric design, but what was the first part of it? I think there's a fair amount of changes in models, but as far as the suspension geometry, I know you mentioned stayed the same. We are using the same engine, so we are able to use all the models in there.
Same drive sprockets.
To add to that, we aren't doing parametric modeling in the sense of what is it, I don't know what, Daniel, PWM, PDM. But we are modeling. I know at least I'm modeling more parts in context. That reduces errors from missing measurements, and it allows you to update drawings faster. So it's not full-blown parametric modeling, but it is modeling in context, which has definitely helped out.
Is the caster and camber on the fronts adjustable on the fly, or is that designed and welded in place?
Camber is adjustable by shims on the outboard side. Caster is not adjustable. It can be adjusted by switching out the upper pickup point on the upright, but that's not something that we've really done in the past. I don't really see it happening this year, but it could be done.
Anything else?
What about business team?
This was a design presentation, so that would be for another time.
Do you have any plans for a business presentation? I mean, for a really competitive business presentation.
We do have a growing business team. This year we do have a number of new members that are part of that. And if there's anything, Hallie is our vice president and kind of leading the business team. And do you have anything you'd like to add?
Well, we've done some really quality recruiting with that. We have 2 county majors who are really excited and really passionate about joining the business team and getting involved, and even a history major there, who has lots of experience with presenting. I'm really excited for this year. I have a lot of confidence that we're going to be very competitive in that these majors, or these members, they're upperclassmen, so they know what they're doing. They've done internships, they have experience, and they can reference, Luca and Reeve, who we still keep in contact with, and also they have me who can kind of give them the experience with that. So I'm definitely excited for this upcoming year. This is going to be pretty cool. No pressure, guys. I believe in you.
Yeah, we're looking forward to the business presentation. We have a new plan for the cost report. Daniel and I are working together with the design leads to make sure that process of getting the cost report is going to go a lot smoother, whereas in the past it's been kind of left for one person to do it. So we have a plan to organize ourselves better.
It was left for the right up.
Yeah, so when do you think, I'm interested in this because we did so well that year. We took second place, second place, and that's doable again. So when are you going to have a business presentation like this that can be critiqued by everybody?
Our plan.
I would say for at least another month or so.
Yeah, another month or two, because the business logic case isn't due until November. I don't remember what exact date it is. So with the real business team, not just like one or two people, I'm actually going to bring them together so that they can come up together with a plan, kind of work out the logistics, actually, you know, come up with the plan, go to other, you know, teachers, and like I currently have a teacher who's willing to help out. He's the economics dean, so he's really going to help out with that. And when we finally have like an idea presentation, like outline structure, we'll be able to go to you guys and have like an official like presentation, kind of get a feel for what we want to do.
As well as just getting all the numbers, the data, the parts, who's working on what. As soon as the engineer, the design leads are completely finished with what they're doing, we can get the accurate numbers for the business presentation according to the SAE rules. So we will have one for you very soon.
Yes, Barrett has one comment, kind of a question. He said, for Stanfield, you might not necessarily lose grip if you still go with wide tires. You'd have to look at the data, but a shorter tire would have a bigger footprint, just a thought.
Shorter tires and, okay.
And then also he asked, have you balanced steering column shaft U-joint angles for speed variation, or looked at difference on and off center steering ratios?
That was something that we messed up. I want to say on the 15 car, the U-joints were out of phase, or they were phased incorrectly, I should say. And then that's something that we corrected on the 16 car. So we'll keep it that way.
Thank you.
Is that motor mounted directly onto the frame and vibrating the entire frame, or is it like rubber mounted, or?
It's rigid. It's rigid mounted, but it's a pretty balanced motor, so it doesn't vibrate too much. You can feel the car while it's running. It doesn't transfer to the chassis as much as you think it would. Cool.
I have a chassis question. Have you or will you have the opportunity to test your honeycomb / composite matrix after the manufacturing of the joints?
Yes, I have planned. We're still trying to figure out when I create the joints, but I have to do a joint test. My plan is to do lap joints and I have to test them.
Okay, yeah.
Another question with the honeycomb. When you're bending, you're routing and bending it, how are you actually holding it in place aside from just the bend? Is there anything else keeping it?
So I'm creating water jetted jigs that go around it. So we'll do one bend at a time, and a jig will hold it in place. And while we cure it with a structural epoxy, and then we're going to do a carbon lap joint afterwards.
Only just the inside or both outside and inside?
We're only routing the one side, so the other side doesn't.
Okay. And have you, for the weight savings, have you also taken into account the high sol or whatever that you're going to use?
Correct.
Anything else?
For safety factor, have you guys calculated what is required as an engineering standpoint, or do you just use the normal safety factor of 2?
For just everything in general?
Yeah, because it could change.
Yeah, I mean, for a number of our leads, I know we do use the material properties and design with the factor of safety. So design to yield.
Yeah, but is the safety factor calculated, or do you just go with a safety factor number?
Why does it got anything on that?
You know what I'm asking?
For the differential system brackets, I know we used 2 to 1. I mean,
yeah, that's the norm.
It was, just not calculated, but did anyone use any different in there?
I use like 2.
Yeah, I mean, once you start compiling all the data, you can actually find areas that you can get a safety factor of like 1.2 for some certain areas.
Yeah, I know for Aero, like we're trying to get as light as possible, so if we're gonna have the lowest safety factor possible.
Yeah.
Our goal for the years coming is to have racks and racks of front wings, so we can break a front wing and put a new one on, so we can make them as thin as we possibly can. We don't want to be afraid to break anything on Aero. We want to have backups ready so we can have them as live as possible. Just break and put on a new one. So we'll be calculating that to see what we can get away with.
Yeah, question. A couple of them. One is, and I think this has been addressed, it would be really nice to get rid of our excess gears instead of having, I guess we have 6 gears, and we could probably get away with 3 gears. And also moving the neutral to one end, all the way down or all the way up, and avoid any kind of misshift, possibly, and weight savings of not spinning the rest of those gears in the engine. But the other thing that concerns me, and I think these guys might back me up on it, is the pedal assembly, regardless of what it's made out of, being mounted to that honeycomb structure. I am concerned just about excessive flex in the floor. Do you agree with this? Remember this. We had a carbon fiber floor once, and while all the numbers seemed to work out that it would be stiff enough, no matter what we did, when you hit the brakes, the carbon fiber floor flexed enough that we couldn't generate enough pressure to lock the brakes. So, all the leads need to kind of look into that and just make sure that that honeycomb floor that you're going to fix that shifter or the pedal assemblies to will be stiff enough to achieve the pedal pressures you're looking for. And these guys will both second me there, I think.
Yeah, because I remember you said you had an increase in hydraulic pressure, right? Between the pedal assembly. Another thing to take into account is every driver wants a linear pressure feel. So if you can track that or graph that out and try to get that as linear as possible, it would be perfect. Because what you don't want is like a degree, you get nothing, and then 2 degrees, you get everything. Yeah. That's what you don't want.
So what's the answer to?
Well, I don't think they have an answer.
No, I know, but what is your position about his point of removing, just keeping 1, 2, and 3 and neutral inside?
I think I did address this with the sponsor who's building our engine for us, and he's going to look into it. It was written down as to the floor pan and the pedals. That's important too. We know the engine's got plenty of power, even if it keeps all the gears.
We visited John Causey Racing on the way back from the last competition this last weekend, and we dropped off one of our engines to them, and they were going to look into what they can do for also reducing weight out of the engine itself, and also taking out the gears and possibly switching up the configuration of the shift pattern. They're engine experts over there, and I'm gonna let them do what they can do, and then we'll work with them, and possibly I'll fly up there again and see what they've accomplished.
But to answer the question of the pedal and the floor panel kind of bending, I'm not sure if that was just, was that actually mounted to something else flat, or was that between like a couple of chassis bars?
It was deflection within it was a combination, so it was a compound cut.
Okay.
So you had a little bit of deflection here, a little bit of deflection here, a little bit of deflection here, and it just adds up. So make sure it covers everything.
Well, that material you use is pretty stiff. If anything, you might have to make a bottom panel to sandwich it. If you're making a big footprint with your co-molling plate, you might have to through bolt it to the.
That's actually what we're doing. Sorry for not elaborating on that. There's going to be bolts, 3 bolts in front, and 2 bolts in the rear. And I'm going to do some FEA. I'm going to do FEA, and because of the fact that it's so easy to manufacture, we're going to create it and see how well it does. So I mean, real life testing is probably the best way to do that. So that's what we're doing.
I was thinking maybe, how we have carbon fiber on just one side of the aluminum in the pedal area, maybe some carbon fiber on both sides of the aluminum might help, as an idea, just to ensure rigidity of that panel.
Is the impact attenuator staying standard, or are we making our own?
Right now it's going to stay standard. We might flip it, because that is an option. It doesn't matter if it's that way or that way. But But it should be standard for now. In the future, we definitely want to look into making our own, but I think we have enough on our hands this year that we just wouldn't have time to get it done. Hopefully next season it'll be our own, so we can make that profile a lot smaller.
Alrighty, anyone else?
I'd just like to add something real quick, something I kind of forgot to mention earlier regarding safety team. This is something that I had started over the summer. Kind of, safety always gets a lot of groans, and I thought would be begrudgingly accepted. I just wanted to say that I was overwhelmed by the response. Those of you that volunteered to help with this over the summer, please. Come on, I know there's more hands out there. I truly was overwhelmed by the response from the people that not just wanted to, but like sought me out to try to be a part of it. So I just wanted to say, while we have our guests here, you guys can be super proud of these guys. I am, and thank you for your support.
I'm proud of you for coming up.
And we changed the gas cylinders to wall thanks to Stevie.
Did they come and visit your chemical storage?
No, no one ever came.
No one ever.
We did call them about the stuff we were using.
Yeah, I know.
And they were
That's resolved.
totally fine with that.
I'm very happy about it. I have to tell you that I met with, last weekend I was in the president's box watching the football game, and I met with one of the board of trustee members, Trustee Rubin. Trustee Rubin was involved with the car about 2.5 years ago, and then he got business issues and he wasn't involved. He saw me, and Fred had sent me the picture of your first place, and I showed it to him right there. And he wants to come back and visit you guys, and he's really excited to help you financially and otherwise. He knows a lot of people also, so I think that's really good. And if you know somebody from the board that is on your team, your support at the university level will be guaranteed. Also, I met with Dorothy Russell, and she said all the good things about you guys, how proud she is of what you have done. And I was lucky enough, she was with the person who's going to replace her next year, Stacy Semmel. Have you met Stacy?
I have not.
Okay. So right there, Stacy said that she's going to have the same level of support. Well, you guys have to formalize it, but she was right there, and she said that she's going to continue. So I was worried about it. Remember we talked about, because you changed the CFO, and you don't know whether the incoming CFO has support for you or not, but she does, and she knows all about what you guys do. So these are two very good items of news that I think is going to be very important for you.
And that's strictly from how well you guys have stepped up the last few years. And like I told you a few years ago, as you keep improving it, more and more people want to be part of a winner. Just like a football team or whatever, you're going to draw more and more help, and the more this program will keep going on. It'll keep getting better.
Yeah, that's great to hear, and we'll stay after for a little while, and we'll exchange information on it.
Just to let you know, the president said that, basically said, he just wants you guys to win. He doesn't care. I'm serious. I mean, he's that kind of an attitude, right? He says FAU is going to be the best, and you guys got to do your part. You guys got to win. I mean, that's his attitude. So.
And again, like he's saying, and a few of you guys experienced it, but what it's done the last couple of years, because of the quality of jobs that you guys are going to be able to get, the people you're going to be in front of, I cannot stress enough. You'll never be in front of this many people hiring at that level the rest of your life.
Also to add, just seeing, Fred took Connor and I around a little bit, and just seeing everything that you guys have, it's amazing the opportunity that's in front of you and the resources that you have that a lot of the other teams in the past didn't. So it's really amazing for you guys.
All good things, all good to hear. But if there's no more design questions, we'll have little tours of our, oh, I'm sorry.
Alright, so Barrett has a lot more here. Alright, first one. Are you using anti-roll bars this year? If I'm remembering right, I don't think you did before.
We never have in the past, and there's no plans to do it this year.
Alright, next one. How is the space frame attaching to the monocoque? Do you have to have some kind of locking hardware?
So space frame is attaching using the 80 thou steel tabs with 5/16 bolts. In the rules, they tell you how many
have.
That's it.
Oh, I see.
So your tires, solid rubber, are they airfilled? Are they kind of rounded or squared off? The corners?
They're hollow. They're not solid rubber.
Standard ration.
Yeah.
Do you have more from?
No,
Okay. All right. Well, I guess if there's no more questions, we'll do a little tour for you guys of our new shop. But otherwise, that wraps up our design meeting. Thank you all for coming.
Good presentation.